Dear students, in this section we are going to discuss about satellites. What is a satellite? A satellite is an object which is revolving around a planet. We are already familiar with the different types of satellites. For the Earth, we know there is a moon. The moon is one of the satellites. For the Jupiter, there are more than 100 moons are there. For the Uranus, it is around 27 moons. For the Mars, there are only 2 moons. So, and also there are a number of artificial satellites. So, we divided the satellites into 2 categories. One is the natural satellites. Most of the planets have got natural satellites moving in the closed orbits. As already discussed, the moon is a natural satellite of the Earth. It revolves the Earth in almost circular orbit of radius 3.84 into 10 raised to 5 km, and the revolutionary period is 27.3 days. Another classification is the artificial satellites. Artificial satellites is a man-made object placed at a height above the Earth and given the necessary velocity so as to revolve around the Earth. At present, there are more than 2,600 operational satellites are there in the space. All of them are revolving around the Earth at different orbits. And we know India has launched the first satellite, that is Aryabhatta, which is the first artificial satellite of India. And next we are going to see what is the orbital velocity. That means all these satellites are revolving around the planet in a fixed almost circular orbits. Okay, so the velocity with which a satellite moves in a closed orbit is called the orbital velocity. Next, we are going to find an expression for the orbital velocity. So let us consider the Earth, which has a mass capital M and radius capital R, around which a satellite of mass small m is revolving in a circular orbit which is at a height small h from the surface of the Earth. We know for an object to executing a circular motion, there should be some centripetal force. In this case, who is providing the necessary centripetal force for the satellite? Here, the necessary centripetal force for the rotation is provided by the gravitational force of attraction between the Earth and the satellite. Then we can write the expression for the centripetal force. We already know mv square by the radius. Okay, here the distance, the radius of the circular path of the satellite is r plus h. Then the centripetal force become mv square. Suppose v is the velocity of the orbital velocity of the satellite. Then v square divided by r plus h. Now this is the expression for the centripetal force. Now the gravitational force. Here what is the gravitational force of attraction between the satellite and the Earth? That we can write according to the law of gravitation. That is capital G, capital M, small m divided by the distance between the centers of the two masses is r plus h whole square. R plus h whole square. Okay. Now we can equate these two because the necessary centripetal force is provided by the gravitational force. Okay. So let us equate this one. That is, therefore we can write m v square divided by r plus h, that is equal to capital G m small m divided by r plus h whole square. Okay, so we can cancel out this small m, and 1 r plus h on the right side can be cancelled out on each side. So the v square equal to capital G m divided by r plus h, or v is equal to square root of G capital M divided by r plus h. Okay. Now this is the expression for the orbital velocity. If g is the small g is the acceleration due to gravity at the surface of the earth, then g can be expressed as capital Gm divided by r square. From that we can have small g r square is equal to capital Gm. Okay, so we can substitute g r square instead of capital Gm in the above equation. Then the velocity, orbital velocity, become square root of small g r square divided by r plus h. Or also we can write, we can take the r square from the square bracket, that is that is r into square root of small g divided by r plus h. Okay. Now this is the expression for the orbital velocity of a satellite revolving around the earth at a distance h from the surface of the earth. Now let us assume that if the satellite is revolving very close to the earth, then the height h will become very small as compared to the radius of the earth. That is, h become very small as compared to the radius of the earth. In such a case, the orbital velocity is called the first cosmic velocity. It is called the first cosmic velocity. Okay. Now we can obtain the expression for the first cosmic velocity from the above equations by putting h is equal to 0. Okay. So h is equal to 0, then the first cosmic velocity v0 is equal to, that we can write in that we can substitute the value of h equal to 0 in the first expression, that is square root of capital Gm divided by r plus h. So we can write capital Gm divided by r. This is the one of the expression for the first cosmic velocity. Also we can do the same procedure in the second expression, that is v is equal to square root of g r square by r plus h. Okay, so if we substitute h is equal to 0, then the equation become g r square divided by r plus h, r plus 0, that is equal to 1 r can be cancelled out, that is square root of g r, square root of small g. Okay, so we can, this is the two expression for the first cosmic velocity. So we can calculate the first cosmic velocity by substituting the corresponding values using either of the equations. Okay, suppose we can substitute the value of g is equal to 9.8 meter per second square, and the radius of the earth, capital R, that you can take as 6,400 kilometer. Then substitute in the second equation, you can calculate v0 is equal to 7.92 kilometer per second. This is the expression for the first cosmic, the value of the first cosmic velocity. Okay, next we are going to see when a satellite is revolving around the Earth, there is another term, that is the period of a satellite. What is the period of the satellite? It is the time taken by the satellite to complete one revolution. It is the time taken by the satellite to complete one revolution. That is called a period. That is capital T. Consider the previous figure. Suppose here m is the mass of the satellite which is revolving around the Earth. Okay, for the one complete revolution, it takes the time capital T, that is its period. So, during that period T, what is the distance traveled by the satellite? The distance covered in a time capital T, that is equal to the circumference. So, during the time capital T, it covers one revolution. That means it completes one circumference. Okay, here with the radius of the circular path of satellite is r plus h. So, the distance covered during the time capital T is equal to 2 pi into r plus h. Now, if we know the distance and time, so what is velocity? Velocity is equal to the distance by time. That is, distance covered is equal to 2 pi r plus h divided by the time taken is capital T. Therefore, capital T is equal to 2 pi r plus h divided by v. V is the orbital velocity. Okay. So, in the previous section, we already have the two expressions for the orbital velocity. So, we can choose the first expression for the orbital velocity and substitute in the equation for capital T, that is equal to 2 pi into r plus h, 2 pi into r plus h divided by v is equal to square root of capital Gm divided by r plus h. Okay. So, the next step we can write 2 pi into r plus h is already there. Here in the denominator it is a fraction, and this square root of r plus h coming to the numerator part, then that become 2 pi into r plus h into square root of r plus h divided by capital Gm. Okay. So, when we take the r plus h into the bracket, then we can write 2 pi into square root of r plus h square. So, that is r plus h square into r plus h divided by capital Gm. So capital T is equal to 2 pi into square root of r plus h whole cube divided by capital Gm. This is the one expression for the period of the satellite. We can also make the expression to make the most. We can have another expression for the orbital velocity. So, similarly, we can have the another expression for the time period. That is, instead of capital Gm, we can substitute small g into r square as we have done in the previous section. So, T is equal to 2 pi into square root of r plus h whole cube divided by small g. Instead of capital Gm, we can write small g r square. Now, this is another expression for the time period of the oscillation, time period of rotation of the, this is another expression for the period of revolution of the satellite. if a body is revolving around the earth very close to the surface of the earth, that means it is moving with the first cosmic velocity, then in that case if h is very less than r, we can substitute h is equal to 0 in the above expressions. Then the period t become, let us express by t0 corresponding to the first cosmic velocity is equal to, the first expression become 2 pi into square root of r cube divided by capital Gm. And also we can substitute this h is equal to 0 in the second expression, then that become 2 pi into square root of r cube divided by g r square. Therefore 2 pi into square root of r by g. Now these two are the expression for the period of revolution corresponding to the first cosmic velocity. As we have done in the previous section, we can substitute the values of capital R and small g, and we can calculate the value of t0. That is, the t0 is equal to, it is around is equal to 5075 seconds. 5075 seconds. Okay. Now this is approximately equal to 84 minutes. Now we are going to see the different types of satellites. When we speak about the broadcasting of the television channels, so we are capable of sitting in our house and can watch the live programs in the different parts of the world. How is this possible? This is possible with the help of the satellites, and that satellite which are help us to watch the live TV channels, live programs. That is, we call them geostationary satellite. Let us see how this helps us or how this works. This geostationary satellite appears to be remain stationary above the surface of the earth. That means if a TV channel is broadcasting some live program, then there is a transmitter, that is, the signal is transmitting to the satellite, and the satellite, after receiving the signal, it spreads the signals through the whole part of the world. Okay, so this uploading of the signal and is distribution of the signal is taking only if the position of the satellite appears to be remain stationary with respect to the transmitting station. Otherwise, it is very difficult to locate the satellite for every time, because the satellite is revolving around the earth. So this happens only when the rotational period of the earth, we know the rotation period of the earth is 24 hours. This should matches with the revolutionary period of the satellite. That means this type of satellite takes 24 hours to revolve around the earth. So it appears remain stationary. It appears remain stationary at a height above the surface of the earth. So in the figure, you can see that the satellite appears to be remain stationary above a particular point, which is at a particular distance from the surface of the earth, and you can see the orbit. The orbit lies in the equatorial plane. The orbit lies in the equatorial plane, and also there is one more condition, that is the direction in which the satellite revolves, it should match with the direction of rotation of the Earth. We know the Earth is rotated about its imaginary axis from the west to east direction. So the satellite should also revolve the Earth from west to east directions. Let us see what are the conditions for a satellite to be stationary. One is the time period should be 24 hours. Second is orbit should be in the equatorial plane of the Earth. And third one, it should be at a height nearly 36,000 kilometers above the equator of Earth. That means this is the height of the orbit, where the time period of the satellite is 24 hours. Only the orbit at this particular height, the orbit should this satellite should have the time period 24 hours. And also, its direction of motion should be the same as that of the Earth, that is from west to east. Next, we can calculate the height of the geostationary satellite. For a satellite to remain stationary, we already know the time period should be the 24 hours. The time period should be 24 hours. So we already have the formula for the period of satellite, that is equal to T is equal to 2 pi into square root of R plus H whole cube divided by small g R square. Okay. So we have to find the value of H. So let us squaring on both sides. We have 4 pi t square equal to 4 pi square into R plus H whole cube divided by g R square, or R plus H whole cube is equal to t square into g R square divided by 4 pi square, or R plus H is equal to t square g R square divided by 4 pi square, taking the cube root on both sides. So when we take the cube root, R plus H cube become R plus H, and on the right side it all times raised into 1 by 3. Okay. Therefore, the height H is equal to t square g R square divided by 4 pi square all raised to 1 by 3 minus capital R. Okay. So we can substitute the values of t, small g, capital R. We can calculate the value of H. So the value of H, for example, t is equal to 24 hours. That is equal to 86,400 seconds. Radius of the Earth is equal to 6,400 kilometer. That is 6,400 into 10 raised to 3 meter. G is equal to 9.8 meter per second square. So when they substitute the values, the expression for the H, and complete the calculation, you will get 35,954 kilometer. Okay, that is approximately equal to 36,000 kilometer. Okay, and also we can calculate the orbital velocity. That we can use the formula V is equal to capital R into square root of G divided by R plus H. So when we substitute the values, and you can calculate, that is equal to 3.081 kilometer per second. So it is found that at a height of about 36,000 km over the equator, a geosynchronous satellite would go round the Earth at the velocity 3.1 km per second. Okay. Then the angular velocity of such a satellite should matches with the rotational speed of the Earth. That means it should complete its orbit once in every 24 hours. That means both have the same angular velocity. Since the angular velocity of the satellite is synchronous with that of the Earth, the geostationary satellite is also known as synchronous satellite. It is also known as synchronous satellite. A single synchronous satellite is on a line of sight. It can cover about 40% of the Earth's surface. So to cover the entire Earth, that means for transmitting a live program in the entire world, we need minimum 3 such satellites, each are separated by 120 degrees. So then it can cover the entire surface of the Earth. Let us see some of the applications of the geostationary satellite. The most important one is the global communication. Next one is the television broadcasting, and also it helps us to in weather forecasting and a number of the defense applications. Let us see, there is one disadvantage of the geostationary satellite, that is that for transmitting the signals to the satellite, we are using the radio signals, but these radio signals take 1/4 seconds to reach and return from the satellite, thus resulting in a small signal delay. This is because here the satellite is in the at a very large height, that is around 36,000 km. So these radio signals take in this much time to reach and return. So this causes a small signal delay. But this is not a problem in the case of the television broadcasting. But when we do the telephone conversation, it makes some difficulty. This delay causes some difficulty. Okay. This is one disadvantage of the geostationary satellite due to its larger height. Okay.